Hello YouTube! Today we're going to be talking about kinematics and calculus. So in particular we'll be deriving the kinematic equations that tend to be basically the only way that AP Physics 1 interacts with motion. We're actually going to not derive two of them. We're going to sort of fundamentally derive the two that you can use to get all the others with algebra. And I will try to post a link to the Physics 1 video where we do wind up actually going into more detail and deriving the other two. It's just kind of a really long process for not a huge amount of payoff because hopefully you're more familiar with the slightly more involved algebra. So, not doing it. All right. So in particular, we're going to be deriving the equations of motion for an object from any of the motion variables as a function of the time. So if you have velocity, you should be able to get acceleration and position. If you have acceleration, you should be able to get velocity and position. And if you have position, you should be able to get velocity and acceleration. You'll be good to go with this if you can derive the kinematic equations, if you can solve a system of equations with the kinematic equations, and if you can take derivatives and integrals and then like translate between those different motion variables with that. So in particular, if you have a situation where you have constant acceleration, this is our one baseline assumption for this. So anytime an object is accelerating at a constant rate, that doesn't mean it's traveling at a constant rate. That would be constant velocity. It means that it is specifically the velocity is changing by a certain amount in a certain direction every second. Then what you can do and how you can write that is that your acceleration as a function of time is just ax, where ax is some constant value. Specifically, because acceleration is the time derivative of velocity and velocity is the time derivative of position, we can take an integral of that equation to get the velocity equation, and then we can take an integral again to get the position equation. So that's our strategy we're going to be working on. This will give us two sort of baseline equations to work from. These will only work if your acceleration is constant. So what that'll wind up looking like, sorry, going to be moving the mic, which is just going to have some unfortunate noises. What that's going to look like for this one is we're starting with acceleration as a function of time is equal to ax, which is the time derivative of velocity and the second time derivative of position. So that's x double prime and v prime. Kind of didn't really leave myself enough room there, so it looks awful. So if we want to find velocity, because this is saying that dv dt is equal to ax, all we have to do is take the time integral, the integral with respect to time, of both sides. And if we do that, we'll just get our velocity equation. Well, the integral of something with respect to time that's just itself is going to be the thing times time divided by the new exponent power, which is 1, so divided by 1. This is overkill. You don't have to do this, but it's going to matter for the next one. Plus your initial value, or your value at time equals 0. Well, this is the velocity equation, and so our initial value for velocity is going to be our initial velocity. So we're just going to go ahead and call that Vx naught. We're using Vx to represent x, the velocity in the x direction. Vx without any naught is representing the current one, which I've at this point said velocity is a function of time instead. Vx naught is saying initial. So anytime you see the naught, that's initial. The subscript x is representing in the x direction. This works just as well for the y direction. We've just picked a direction and called it. If I want position, so this is sort of actually, before we move on, this is our first equation. So our first kinematic equation, and this only works for constant acceleration because that was our baseline assumption, is that velocity is equal to acceleration times time plus initial velocity. If we then want an equation for position, we're basically going to do the same thing, where we say that this is equal to dx dt. And to get that one alone, we're again going to actually, I'm going to rewrite this. So dx dt is equal to ax t to the first plus vx naught. If I want to just have x, I'm going to have to integrate with respect to time on both sides. When we do that, integral of dx dt is going to be just x as a function of time. That'll equal, integrals distribute across addition because they're sums. So multiplication distributes across addition. Integrals are basically multiplicative sums, so they distribute across addition as well. And we'll wind up with, actually I might as well just write it out, integral of ax t dt plus the integral of vx naught dt. So when we add those together, what we'll get is 1/2 ax is a constant, so it just stays. Time is not a constant, so that one has to have its power increased. So it goes to the 2, which is where the half comes from. As a double check, if we take the derivative of this, we'll get tax times 1/2 times 2, which is axt, which is what we started with, so we're good. We've done the integral correctly. Plus vx naught times t, again divided by the 1 and to the first power, but those are basically not there, plus some constant representing our initial value. And let's call that our initial position, x naught. So that's x as a function of time. This is our second equation. Between these two equations, you can theoretically solve for anything. Now, part of the problem is you'll have to use a system of equations. So this first one is especially useful if you don't care about your position at all, because this equation doesn't use position. So if you know 3 of the 4 variables in this one, you can use that to solve for the other one. So if you don't know your position, this one is great. If you look at this one, if you don't know anything about your final velocity, this is great because this doesn't include a final velocity. Generally speaking, this is a system of 2 equations with 5 variables. So you're allowed to be missing 2 of the 5, meaning if you ever know all 3 things, the 3 being displacement, so if initial final position would be another way to say that, velocity, acceleration, or current velocity, acceleration, final velocity, or time. If you ever know any of those 3, you're good to go, and you could theoretically use these to solve for the others. But it's really easy if we have just one equation that's missing the thing we don't care about. And so it'd be nice to get another 2 equations with 2 more things that we might not care about. We're not going to get one without vx naught, because you could just take the vx one and think of it as going backwards in time, and think of this as your final velocity, the acceleration as being negative, and that would let you solve it that way as well. Alternately, that one tends to be pretty straightforward to just use this equation to get final velocity, and then you can get whatever else you're missing, or one of the other equations to get final velocity. If you do the derivation by solving this equation for time and plugging it into this one, that'll get rid of time. When you do that, what we'll get is that your final position is equal to, and I'm actually going to say final position minus initial position, which is the same thing as displacement, is equal to vx naught plus vx divided by 2 quantity times time. And the reason that I like this equation a lot is because it actually makes a decent chunk of sense if you look at the little pieces. This right here, if you have a linear function, is your average velocity. So what this is saying is if you take your average velocity and you multiply by time, that'll equal your displacement. Well, yeah, good. That's our average velocity equation. Now, this again only works with constant acceleration because this won't equal average velocity in any other case. But for constant velocity, this equation, to me anyway, makes a lot of sense. It's also pretty nice because the algebra is not too bad for this one. So if you don't know anything about acceleration, this one's great. If instead you don't know anything about time, the equation winds up looking something like this, where you'll get final velocity squared is equal to initial velocity squared plus 2 times your acceleration times your final position minus your initial position. Again, you get this by plugging the two equations into each other. I said it backwards. This one's what you get if you solve for time. This one's what you get if you solve for acceleration. The algebra for that is actually kind of interesting, but takes a while. So if you are interested in that, I will, again, try to remember to post the link to the AP1 video where it happens once we do that for AP1. So there's your derivation. We should actually do an example problem that uses them, though. So let's say we got a situation where a car slows down to stop. It takes 10 seconds to do it, and it goes 30 meters. So A, how fast was the car originally going? B, what was the acceleration of the car? So copying down our givens. Generally speaking for these, if you see a kinematics problem, just creating a nice little table where you're keeping track of anything can be a big help. So our possible variables are displacement, which kind of shortcuts all of the stuff with x and x naught, especially when you have two objects. It might be better not to do it by displacement, but for now this one will definitely work. Vx naught, Vx, acceleration, and time. The two things we don't know here are how fast the car was originally going, so Vx naught, or the acceleration, so leave A as a variable. We know that our displacement is, we know that our displacement for this one is 30 meters because we travel 30 meters in the time that we're stopping. We know that our final velocity for this one is 0 because it winds up stopping. We also know that our time for this one is 10 seconds because it needs to stop. All right, so let's actually solve this out. Well, if our first question is asking us for how fast it was originally going, or Vx naught, then we should take an equation that has Vx naught and doesn't have the other thing we don't know. So we're looking for an equation with no acceleration, because that's not something we're being asked about and we don't know it. The only equation that's got that is that our displacement is equal to our final velocity plus our initial velocity divided by 2 times our time. I'm going to go ahead and solve this one first, although anytime something's a 0, it makes your life a lot easier, so I'm going to go ahead and plug in a 0 before I solve it. What I'm left with is x naught equals Vx naught over 2 times time. Multiply by 2 to get rid of the 2 on the bottom, divide by time to get rid of the time, multiply by 2, divide by time, and we're done. 2 delta x over t is equal to Vx naught. We've still got our 2. Delta x was 30. T was 10. That gives us out a final answer of, 6. Because it's 30 over 5 meters per second. And positive. So initially we were traveling forward at 6 meters per second. For B, it's a very similar process. This time we're looking for acceleration. We have everything else, so it's, for me, easiest to just pick the equation that's got the least algebra involved, which is the first one. Our final velocity is equal to our initial velocity plus acceleration times time. If we want to get acceleration alone, again, it's a little easier if we plug in stuff that's 0. So 0 is equal to Vx naught plus AT. Subtract off Vx naught from both sides. Subtract off Vx naught from both sides. That'll give us minus Vx naught equals acceleration times time. divide each side by the, oh geez, I just realized that all the accelerations are supposed to have little x's on them because the College Board hates me being able to write things efficiently. Divide each side by ax, divide each side by ax. And what we'll get is that negative vx naught divided by ax. Oh, we're solving for ax. Whoops. Divide by time, divide by time, divide by time. So we'll get vx naught divided by time. And I'm actually going to completely rewrite this, is equal to our acceleration, which in this case is minus in front of a 6 divided by our time of 10. So our acceleration was negative 0.6 meters per second squared. In this case, the slowing down was negative because we chose to make our initial velocity such that it was positive by saying we had a positive displacement. If we had picked that the object was originally going backwards, we would have had a negative acceleration, negative displacement, a negative initial velocity, and a positive acceleration. Would have been totally fine. Would have just meant we defined whatever direction we were going at the beginning as negative. All right. I do want to sort of talk about how to do this if your velocity or your acceleration is not constant. And basically you do the same approach. It's just that you don't have those specific equations that you could theoretically memorize to solve it. So you have to actually do the same approach every time to basically rederive everything and build a system of equations from there if you actually need to. So generally speaking, you'll be using derivatives and integrals to translate between the equations that they give you and the equations that you actually want to solve for the thing they're asking. I think this one makes the most sense if we do it as an example. So let's just do it as an example. So this is problem 1. This is problem 2. So for problem 2, we have an object with a velocity curve. Velocity as a function of time is equal to a t squared minus bt. So we're throwing in some stuff with variables just so you can get a little more used to that. Not necessarily what people are going to be used to. Give all answers in terms of a and b. So a and b are allowed, t is not. Where is the object after 5 seconds of travel if it begins at the origin? So we want to find x at time 5. And b, at what time is the acceleration twice the original acceleration? So we want to find the time when a is double the initial acceleration. So to do that for a, meaning part a, we'll need an equation that actually reflects what position is, because position isn't anywhere in our first equation. But we can take our velocity equation and take an integral, and that will give us our position equation, because velocity is equal to the time derivative of position. So if I just take this and I integrate both sides with respect to time, what I'm left with is a t squared. The 2 will become a 3 for the power. I need to drop that 3 down into a fraction so that if I retake the derivative, times 3 gets rid of the 3. We're left with a 2. We're all set. Minus b, still a constant, so that one will stay. T to the first, I need to increase the power by 1, and then drop that down into a fraction, so 1/2, plus some constant representing the initial position. But we're told this thing starts at the origin, so that initial position is 0. And that'll equal x as a function of time. We're asked to plug in 5 and find out, oh geez, I need to remember, sorry about that. Take a sec, copy it down. It's actually the right size now. Habits are hard to form, especially good ones. We're asked to find what the position is at 5 seconds. So all we have to do is plug in 5, and that'll give us the position at 5 seconds. So in this case, we'll get 1/3 times a times 5 to the 3rd minus 1/2 times b times 5 squared. Will this be a messy answer? Oh yeah, absolutely, but that's totally fine. That's 125 over 3 times a minus 25 over 2 times b, and that's our position at 5 seconds, and there's our answer. Is it pretty? Nope. Is it done? Yep. For B, it's going to be slightly more work. So for B, we have to find an equation for acceleration because they're asking about acceleration. Well, acceleration is equal to the derivative of velocity with respect to time. So if we take our velocity equation and we take the derivative with respect to time, our velocity equation being at squared minus bt, that'll give us our acceleration equation. So our acceleration equation for this one is equal to, as a function of time, is equal to 2at minus b. Now the problem asks us what the acceleration is going to, when the acceleration is going to be double the original acceleration. I need to figure out what the original acceleration was if that's going to work. So I need to actually plug in t equals 0. If I do that, that'll give me ax naught. Well, ax naught, in this case, once we plug in t equals 0, all this goes away and we'll just get negative b. So we need to find the time when our acceleration equals double ax naught, which is negative 2b. We just have to double this acceleration. So what we can do is plug in negative 2b for our acceleration into our acceleration equation. Negative 2b equals 2at minus b. And we're just solving this for t, and we're done. Add b to both sides, add b to both sides. That will give us that negative b equals 2at. Divide each side by 2a, and we're done. Sorry, it got very small and very cramped. Negative b over 2a equals t, and there's our answer. And that's it. You just have to leave it in that form because it's asked for it in terms of b and a. So in particular, taking a second, looking back on what we did there, once you have one of the equations for one of the curves, if they're asking about one of the other types of variables, we had a velocity curve and we were asked about position, totally fine. We just have to swap it over to a position curve, position function, a function for position in terms of time. We'll do that with an integral if we have velocity. We do that by taking the integral twice if we had acceleration. If they're asking about acceleration, take derivatives until you get to acceleration. From there, hopefully you're good. We're going to talk next time about how we would find minimum, maximum, how long something's doing a thing for, how you would find like total distance traveled or things like that, because that is a bit more of a pain. But for now, that's plenty to practice with. So throw any questions you got in the comments, and goodbye, YouTube.